Hello, everyone. In this video, we're going to look at example 1 in section 5.6, where we're going to apply the midpoint and trapezoid rule to approximate an integral. So because these rules should start to feel fairly familiar, since they are similar to the ways in which we've estimated integrals using rectangles, I encourage you to pause the video and try to work out these examples on your own first, and then continue watching to compare. All right, let's get started. So at first it tells us to use the midpoint rule and then the trapezoid rule to approximate this integral. Okay, so we have two different graphs here set up to help us draw in the rectangles or trapezoids we're going to use to approximate this integral. All right, so starting with the midpoint rule. So we'll do midpoint here first. Let's go ahead and draw in these rectangles. So notice that we're using n equals 3, so that means the number of rectangles we are going to use, or the number of trapezoids, is going to be 3. So since our integral takes place from 0 to 6, those are the bounds of our integral. I'm going from 0 to 6, and we want to use 3 rectangles. We can see that the width of the rectangle, the change in x, is going to be that 6 minus 0, which is 6, the length of our entire interval, divided by 3, the size of our, or the number of our rectangles. So 6 over 3, that gives us 2. So let's go ahead and draw in those rectangles. All right, so I'm first going to draw in our separators here, and then we'll determine how high we should draw these. All right, so again, we're going to be using the middle point of each interval to calculate that height. So that means we're going to use this point here at 1. I'll erase so that we can see. We're going to use 1, 3, and 5. So then if we're just drawing in these rectangles, the height of our first one would be this high. We can draw that in, a rectangle like that. The height of our second rectangle would be at the middle of that second rectangle, would be this high. And the height of our final rectangle would occur at that 5 value, so about like this. Awesome. Okay, so now let's go ahead and actually compute the areas of these rectangles. So let's practice using the notation that we saw in the first part of this section. So we want to compute the midpoint approximation using 3 rectangles. So that would be m sub 3. So recall that formula is the change of x times the value of the, or rather the height of each rectangle, which occurs at what we were calling x sub I bar. So this x, this 1 here, is what we were calling, if I can get my pen back, is what we were calling x sub 1 bar. This 3 is x sub 2 bar, x sub 3 bar. So just using notation, this would look like f of x sub 1 bar plus f of x sub 2 bar plus f of x sub 3 bar. All right, so let's just fill in the values that we have. So we know that delta x is 2, and then our f of, or our x sub 1 bar is 1. F sub 2 bar, x sub 2 bar is 3, and then our final evaluation is at 5. So in order to determine what these values are, we consult our integrand, our f of x function. So we'll call this f of x, is the square root of 40 minus x squared, square root. All right, so what does that become? That becomes 2 times 40 minus 1 squared, square root, plus 40 minus 3 squared, square root, plus 40 minus 5 squared, square root. So we can work this out further. So we get 2 times the square root of 39 plus the square root of 31, because 3 squared is 9, plus 5 squared is 25. So 40 minus 25 is 15. So we have the square root of 15. All right, so if we plug that into our calculator, we get something near 31.37. All right, so again, the midpoint rule. Awesome, nice work. So now let's take a look at the trapezoid rule. So to start, let's go ahead and draw in those trapezoids on our graph. So we're still using 3 shapes, 3 trapezoids. So that means our delta x is still going to be 2. And so we can draw in those trapezoids here. So my separators are at 0, 2, 4, and 6. And then how do I connect them? Well, a trapezoid, we're just connecting the 2 endpoints where they hit the graph. So like this. All right, looking good. So now we need to write out the formula for how we would compute the area of those trapezoids. So using our notation, that is T sub 3. And recall, we can look back at the formula that we got when we were computing the trapezoid rule, and we get delta x times, we'll call this x sub 0, x sub 1, x sub 2, x sub 3, f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus just f of x sub 3. So recall the first and the last evaluation, we just have one of them, but we have repeats of all of the inside dividers. And make sure you watch that first video if you need some review on that. So what does that look like for us? Well, delta x is 2, so we have 2 of f of 0 plus 2 times f of 2 plus 2 times f of 4 plus f of 6. So let's go ahead and plug those values into our function f. So we get 2 times the square root of 40 minus 0 squared plus 2 times the square root of 40 minus 2 squared plus 2 times the square root of 40 minus 4 squared plus the square root of 40 minus 6 squared. So we're doing these types of problems since we have so many little details going on. It's really important just to take your time, look over your work, take it slow. I could put another parenthesis here if I wanted. All right, so if we put this into our calculator, we get something close to 30.12. All right, so in summary then, for our midpoints, we are getting an approximation of 31.37. And for trapezoid, we're getting an approximation of 30.12. So now let's finish this example off by looking at part B. So part B asks, is M3 an over or underestimate of the integral? How about T3? Then after that, we need to use these observations to give an even more improved estimate of that integral. So let's look at both of these. So take some time just to look at your own rectangles and trapezoids and see if you can determine if either which one is, or for each, what is an over and under estimate. So one thing we can observe is that in our trapezoids, all of these trapezoids are under the area of our integral, or are less than the area that we're actually wanting to approximate. So we missed this area here. So that means our approximation is actually an underestimate. So T3 is an underestimate. So we can go ahead and write that out. So T3 is an underestimate. Let's give a reason why. It's an underestimate of the area under F because all three of those shapes, all three of those trapezoids lie below the curve F. All right, so now let's take a look at the midpoint then. So it's a little hard to tell here, but what we can do is compare for each rectangle the area that we're missing with the additional area that we included. Area we're missing, extra area we included, area we're missing, extra area we included. So if we study this and maybe drew an even better or more accurate rectangles, we'd see that this blue area that we're shading is a little bit larger than each of the green areas. We can kind of see that too, because this curve, the way that it decreases is it gets further and further. The decrease gets stronger and stronger, meaning that rate of change gets larger and larger or more negative. The values here, the area here is larger than the area here. So that means we have more blue area than we do green. So we're counting over the amount of area that we're actually wanting to approximate here. So let's go ahead and write that down. So M3 is an overestimate of the area or of the integral. And why is that? Because the extra area we include is larger than the area we didn't include, which we wanted to, or which we were approximating in each rectangle. Now, I do want to point out that this is not always the case. It's not always true that the trapezoid rule underestimates and the midpoint rule overestimates. And we saw this when we used the left and right endpoints of rectangles. It really depends on the shape of the curve. What is an over or underestimate? All right, so now let's follow up with the second part. So use these observations to get a more improved estimate. Well, so because T3 is an underestimate, it's a little less than the integral, and M3 is a little bit over estimate of the integral, then to get a more exact value or approximation, we can just take an average. So average out this over and underestimate. So what does that look like? So we're going to take an average of T3 and M3. So what does that look like for us? So let's recall we have T3 coming in at 30.12, M2 coming in, or M3 rather, coming in at 31.37 divided by 2, which gives us 30.75. And again, that's because we took an average of the over and under estimates. Awesome. All right, great work, everyone, looking through this example.